You're looking at one of nature's most spectacular and, let's be honest, destructive forces. I mean, a single flash of lightning can tear across the sky, unleashing an unbelievable amount of energy in just a fraction of a second. For most of history, we could do nothing but watch in fear. So the question is, how did we go from cowering inside to actually taming this celestial fire? Well, let's dive in and unravel the incredible science that literally tamed the sky.
To kick things off, I just want to put one number up, 53,000 degrees Fahrenheit. Now, take a guess. What on earth could possibly be that hot? It's not a furnace, it's not the core of a planet. That is the temperature of the air inside a typical lightning bolt. And here's where that number gets completely mind-bending. That 53,000 degrees makes a lightning strike more than 5 times hotter than the surface of our sun. Yeah, you heard that right. We're not talking about a little spark here. This is an incredible force of nature, capable of melting solid rock in the blink of an eye. So with that kind of raw, unimaginable power, you can see why for most of human history, lightning was seen as something, well, supernatural. Before we had science, we had myths and a whole lot of fear to try and explain this terrifying force from the sky. For centuries, people were convinced that lightning was a weapon of the gods, some kind of divine punishment. In medieval Europe, they actually tried to fight back. It was common practice to ring specially blessed church bells during a storm, bells that were even inscribed with the phrase fulgura frango, which means I break up the lightning. Of course, the tragic irony is that climbing up into the tallest building in town to ring a giant metal bell during a thunderstorm is probably the most dangerous thing you could possibly do. And the numbers prove it. In one 33-year period alone, 103 bell ringers were killed at their posts. But this is where the story takes a huge turn. We go from superstition to science, all thanks to one key figure who dared to question the heavens himself, Benjamin Franklin. He noticed the similarities between the little sparks from his electrical gadgets and the massive bolts in the sky, and he started to wonder, could they be the exact same thing? So in 1750, Franklin proposed an experiment to test this wild idea. 2 years later, he did his legendary kite experiment, drawing a spark from a key tied to the wet kite string. And this wasn't just some cool trick, it was definitive proof that lightning was electricity. But this was incredibly dangerous stuff. Just 1 year later, a physicist named George Richmond was killed in Russia trying to do a similar experiment. The real turning point, though, came in 1777. A skeptical crowd in Siena, Italy watched as a huge lightning bolt hit their City Hall tower and was guided harmlessly to the ground by one of Franklin's new inventions. The game had officially changed. Now, Franklin's original idea, in his own words, was that a sharp point would silently draw out the electrical fire from a cloud, basically preventing a strike from ever happening. It was a brilliant idea for sure, but it turns out he was only half right. Because while a rod can dissipate a tiny bit of charge, its real job is way more dramatic. And to understand that, we need to understand the beast it's trying to tame. So, how does this electrical fire even get started in the first place? Well, it's this incredible, chaotic dance of physics happening miles above our heads, right inside a storm cloud. Okay, let's break this down, because what's happening in there is like a giant natural generator. You've got this wild mix of rising water droplets and falling ice crystals all smashing into each other. As they collide, electrons get stripped away. It's kind of like the static electricity you get from rubbing a balloon on your head. This process separates the charges. The lighter positive particles get swept to the top of the cloud, and the heavier negative particles sink to the bottom. The cloud basically becomes a giant polarized battery hanging in the sky, and that massive negative charge at the cloud's base pushes away electrons on the ground below it, leaving the Earth with a strong positive charge. The stage is now set for something big. And here comes the final act. First, a channel of negative charge, called a step leader, starts to zigzag its way down from the cloud. As it gets closer, that positive charge on the ground reaches up to meet it. This is called a streamer, and it rises from the tallest objects around, trees, buildings, or, you guessed it, lightning rods. When that leader and streamer connect, boom, a complete electrical pathway is formed. And then comes the main event, the return stroke. A massive, unbelievably fast surge of current flows along that path, and that is the brilliant flash we see as lightning and the explosive shockwave we hear as thunder. So, if the lightning rod isn't preventing the strike, what's it actually doing? It's basically volunteering to be the meeting point for that leader and streamer. Today's lightning protection systems are the highly engineered descendants of Franklin's simple rod, and they're designed to safely handle that incredibly powerful return stroke. The best way to think of a modern lightning protection system, or LPS, is not as a shield but as a superhighway for electricity. Its job isn't to stop the lightning, it's to grab it, control it, and give it a safe, easy, unobstructed path straight into the ground, completely bypassing the building and everyone and everything inside. So let's take a look at the key parts that make up this highway.
First up, you have the strike termination devices, or air terminals. Think of these as the on-ramps to our superhighway. These are the direct descendants of Franklin's original rod. They're strategically placed all over a roof to be the most inviting target for a lightning strike, essentially yelling at the bolt, "Hey, hit right here!" So once that lightning is intercepted, all that energy has to go somewhere. It travels down the main lanes of our superhighway, these thick, highly conductive copper or aluminum cables. And this is critical. Safety standards require at least 2 separate paths to the ground. It's like a multi-lane highway designed to safely divide up the immense electrical traffic from the strike. And of course, every highway needs an exit. That is the job of the grounding electrodes. These are long, copper-clad rods driven deep, like 8 to 10 feet deep into the earth. They provide the final, safe destination for all that energy. The ground itself acts like a giant electrical sponge, just soaking up the entire charge without any harm. But what about traffic trying to take a dangerous, unplanned exit? That's where bonding comes in. The whole system is physically connected to a building's other metal components, like pipes or ductwork, to prevent a dangerous side flash from jumping sideways into the building. And for all our modern gadgets, surge protective devices are like the system's shock absorbers, stopping that massive electrical surge from completely frying everything you have plugged in. All right, so having all these parts is great, but how do we actually know that they're installed correctly and are going to work when a 53,000-degree bolt of lightning comes calling? Well, that's where standards, testing, and certification become absolutely essential. In the US, the official playbook for lightning protection is a document called NFPA 780. It's the national safety standard. And then you have organizations like UL Solutions who provide that critical third-party inspection to make sure the system on your building actually meets that standard. And trust me, this isn't just about paperwork. It is a literal guarantee of safety. So how do they check the most important part, that connection to the earth? Engineers use a method called the fall of potential test. Now, it sounds complicated, but the idea is actually pretty simple. They isolate the grounding system, run a small, controlled current through it, and then measure the resistance. The result tells them if that exit ramp on our superhighway is clear enough to handle the full force of a lightning strike.
And why is this level of independent testing so incredibly important? The answer really comes down to one pretty startling number, 85%.
That's right. According to UL Solutions, a staggering 85% of the systems they inspect for the very first time require some kind of repair to actually meet the national safety standard. That just underscores a critical point. Just having a system installed isn't good enough. Without that independent verification, there's a very high chance it won't work when you need it most. So you see, certification isn't just a sticker you put on a building. It means the system was designed correctly, it was installed by trained professionals, it uses quality parts, and it's been independently checked to make sure it works. It's the final step that turns a bunch of metal parts into a genuine life-saving safety system. It's peace of mind. I mean, when you step back and think about it, the journey is just incredible. We went from seeing lightning as a stone axe hurled from the skies to understanding its physics so well that we can literally build a superhighway for it to ride safely into the ground. It's just a remarkable story of human curiosity turning fear into understanding, and then turning that understanding into safety. So what part of this whole story surprised you the most? Was it that lightning is 5 times hotter than the sun? Or maybe that 85% of systems fail their first inspection? Let me know your thoughts in the comments below. We make explainers like this one every week, breaking down the science that shapes our world. So if you found this interesting, do us a favor and subscribe so you can join us for the next one. Thanks for watching.